Welcome back. In this next two slides, we'll perform a DTFS on a sinusoid, which is this signal over here, and then which is simply a sine pi over 4n. We then find the C case of this sinusoid, find its representation, and then convert it into DTFS. So in this example, as in the previous example, because this is a cosine, we can use inspection. We basically convert this cosine into sum of complex exponential, and then by inspection we already see that this xn is simply the sum of two complex exponential. One is at pi over 4 radian per sample, and the other one is at minus pi over 4 radian per sample. These are the coefficients associated with these two complex exponentials, and this is the DTFS representation. If you have issues, go back to the previous slide and show and study again how we have done this inspection method to find the coefficients. So this is the C associated with the positive k, and this is the C associated with the negative k, and of course we have to go ahead and find what is the value of k by finding the period n and associate the k to produce pi over 4 radian per sample. If we are not interested in the representation as k, but we are using omega instead, then here we simply write omega equals to pi over 4 and minus pi over 4, and we store the magnitude over here, and then we store the phase over here. So we have found the coefficients for positive pi over 4 as a over 2, so we have the magnitude a over 2 here. So this a over 2 is simply this a over 2. At this frequency pi over 4, we have minus pi over 2, so we have minus pi over 2 here. So these two lines is simply these two coefficients, a over 2 for magnitude and minus pi over 2 for the angle. Now I'm going to sketch in green now. What about these two lines? This on top is the magnitude, which is also a over 2, so it is this a over 2 over here. And then what about the phase, which is plus pi over 2, which is j pi over 2 here. So these values, now let me sketch again for you in green. A over 2 is the magnitude, and the phase is pi over 2 at the angular frequency minus pi over 4. So along the horizontal axis is minus pi over 4 and minus pi over 4. I also show you the value of k. K is actually equals to 1 because we are using n equals to 8. So 2 pi over 8 is pi over 4, which is the angular frequency we need, by multiplying k equals to 1 and capital N equals to 8. Now, the problem was to find the DTFT representation. So to find the DTFT representation, remember we need to multiply the CK by 2 pi, and we put it at the delta omega equals to minus 2 pi over nk. So remember, ck is a complex number. When we multiply by a real number, we're only changing the magnitude and not the phase. So 2 pi times a over 2 becomes a over 2 times 2 pi, which is a times pi. So in the next slide, you'll realize that for this magnitude plot, the value becomes a times pi at the same angular frequency, which is at pi over 4. But this now has become a delta function, so it changes into an arrow. So the previous slide, this point becomes an arrow. This point also at minus pi over 4 becomes an arrow over here. So the magnitude now is changed to arrows at the same angular frequency. The phase over here is minus pi over 2. Look at the one behind, which is at minus pi over 2 at angular frequency pi over 4. Angular frequency minus pi over 4 is plus pi over 2. So there is no change except with the arrow for the phase. So this is the x omega, where omega is radian per sample. It is continuous, and because this is a continuous function, to represent something at that particular frequency, we are using the delta function. Okay, and so this is the DTFT of the periodic signal xn, and xn of course is our cosine over here. Okay, that's it. Thank you.